Thanks very much. Thanks for the invitation and having me here. And yeah, I also work on dark matter like what Professor Hong does, although I do a very different way. Today, I'm going to share with you some of the research I do. And I'm an observational astrophysicist, which means I spend a lot of time on telescopes, observatories all over the world. This is one of the movies that I think I spent over 200 nights there when I was a graduate student in Chile. Yeah, if you get a chance to go there, you definitely will see these skies. And today I'm going to talk about how we as astrophysicists use telescopes to study dark matter. And I also mention a little bit of the black hole. So I'm going to start. So this is, I'm going to start with because this is the audience of a lot of physicists. So I'm going to start with the way or the hunt of dark matter through more other particle physics way. So this is a diagram showing the dark matter and the standard model particles on the right and dark matter particle on the left. And for particle mass by the weak scale at GeV and to the TeV level, there are several ways that going on for the hunting of dark matter. For example, if you go this direction for standard model dark matter and the standard dark matter interaction, you may make produce some of dark matter. This is like the production, what do we call, and I know that some of the experiment probably at LGC is working on that. And if we go this direction, we hope one dark matter interact with the standard model particle and then generate some standard model particle signal that can be detected. This is a lot of this underground experiment for direct detection. And the few physicists in the physics department here is working on. If we have, and this is a common plot you might see. One x-axis shows the mass of the particle or the WIMP particle. So these are the weak interacting massive particle. And on y-axis here shows the cross section. So you can think of the chance of a dark matter particle interact with a standard model particle. And this is kind of different of the limits right now get from different experiments. And some of you probably working on that. And if going this direction, I'm sorry. Oops, what happened? Is it too far? Okay, if going this direction, then we were hoping dark matter and dark matter will have some interaction and annihilate or decay. And this is something called indirect detection. And things like the Fermi-LAT satellite in the space are trying to measure some signal from the standard model, like gamma ray or X-ray, and hoping that's coming from the dark matter annihilation. So these are what physicists does. I don't actually do any of that, but I want to point these out. There are a variety of ways of doing dark matter study. My research a bit connect to the indirect detection I will mention later. But what do we do? Oh, this one I'll come back later. And what we do is to use the telescopes all over the world to study the nature of dark matter. And here are just a list of different experiments, either ongoing or future ones that in yellow. And there's some doing imaging of the sky, some taking spectra of the galaxies and doing some high resolution imaging from the space or from the ground. So I'm going to talk about how we do those, how we use them to study the dark matter. But before that, let's take a look, step back and to see what we have learned about dark matter from astrophysical observation. This is something you probably have learned from the class. So first, we learned that dark matter is not baryon. Dark matter consists 25% of the universe. And the observational evidence for that is CMB, stands for cosmic microwave background, and the BBN is the Big Bang nuclear synthesis. So this is kind of one of the most beautiful theory that fit into the data, model fitting into the data, the lambda CDM model. Lambda stands for dark energy, that is about 70% of the universe. CDM stands for cold collisionless dark matter, which is about 25% of the dark matter. And the data in the model with 6 parameters and all these portion of different dark matter and dark energy and also the ordinary matter kind of fit the data very well. So that's what we learned observationally already. And another thing we learned is dark matter cannot be hot. That means that in terms of mass, it can't be below, it cannot be below keV level. It has to be at least a few several keV. And that's just coming from observational evidence called a structure formation. So this is a picture showing you the large scale structure of the universe. The top and left panel in blue are from observation. Each dot here is a galaxy that observed by several different surveys. So it's 2DF survey here, it's Sloan survey here. So you can see the structure that in our universe, these kind of filamental kind of structures, these are from observation. And the bottom and the right panel are coming from simulations. And that's assuming that the dark matter is not hot. So if it's hot, then you can think of the structure formation, the galaxy formation is top down. It formed the big thing first and then get fragmented to small pieces. If it's not hot or it's cold, then it's a bottom-up model that small things form first and then go growing into big one and have these kind of formations. So this is a CDM-based galaxy simulation and matches with observation very well. So this is all what we have known. But even we rule out hot dark matter, we know dark matter exists. This is what the theorists give us in terms of the paradigm of possible dark matter candidates. It's a very nice summary paper. I highly recommend you to take a look if you're interested in this topic. But just give you guys idea about what kind of possible dark matter candidates. So this, you can think of the outer ring as kind of the candidates, and the inner one is like different kind of models. So the weak scale and supersymmetry is like the WIMP that a lot of ground-based and space-based indirect and direct detection search. But there's also other ones like warm dark matter going in this direction, neutrino, or if the dark matter itself is interacting, self-interacting. If the dark matter is microscope, like primordial black hole. I'll mention all of these later in my talk. So there are a bunch of these and modified gravity. So there's way more than just a WIMP, which is in this weak scale branch, right? So for astronomer or astrophysicists, we are trying to study all these possible dark matter models to prove, to dispute or to prove one or the other model through observations. And I'm gonna give you a few examples. And in terms of the mass of the dark matter, so this is the range of dark matter, possible mass of the dark matter particle. You can see the smallest is at ZeV, which is 10 to the minus 21 eV. The largest is like black hole at 30 solar mass is 10 to the 67 eV. Right, so it's a range of like 80 order magnitude. And that's what we don't know about dark matter. And here you give a few, I put a few candidates here, and also these connect to the previous figure where they are in terms of their mass. And so what we study, for me, what I do is I use the distribution of dark matter in our universe to understand the composition of the dark matter, to understand those. And I'm gonna give a few examples, but specifically the thing we do is called the small scale structure of dark matter. We wanna study the dark matter behavior in the small structure, a small scale structure, because the larger scale structure, I've already talked about that earlier, right? We already know the larger scale structure rule out the warm or the hot dark matter already, but there's still a lot of other variety of dark matter model we have. Okay, so what I particularly work on is something in our Milky Way. So this is like a simulation of our Milky Way. This is the visible part that we see like a Milky Way disk there. But there, if you look at the sky with, like if you can see dark matter, this is what we think of the distribution of the dark matter in our Milky Way. So there's a big dark matter halo that the Milky Way residing in. And there's just tons of thousands to even maybe millions of these dark matter subhalos around our Milky Way. Some are big and some are very small. So the big one are these kind of things. You might heard, or you may even see if you have ever get a chance to go to the southern hemisphere. This is a large magenta cloud. Again, if you ever get a chance to go to the southern hemisphere, you will see these kind of little smudges. These are the satellite galaxies in our Milky Way. It's our nearest neighbors. And so these are the galaxies that reside in these kind of we call them subhalo. You can think of the dark matter clusters, and the most massive dark matter form a cluster form like Milky Way, like galaxy. And then the smaller halos, it's because it's surrounding the Milky Way, we call them subhalo, and they can form these kind of galaxies like we call dwarf galaxy or satellite galaxies of our Milky Way. And there's also small ones like these. So these are also galaxies, but you can actually never see them just with a telescope, with your naked eye, or even with telescope, obviously from image. What we can tell is we can measure individual stars there. I don't know if you can see the circle I have there. We measure individual stars there. We confirm these stars are all moving together. We also can use kinematics to measure the total mass of those galaxies. And we know that there are dark matter dominated in these galaxies. So a lot of science I do is with these galaxies. They are the satellite galaxy of our Milky Way. So our Milky Way has a big disk galaxy, and there's these small dwarf galaxies around our Milky Way. And how we use them to study the nature of dark matter. The first thing we do is we try to use these satellite galaxies to count the number of dark matter subhalo. So here, the thing we're trying to differentiate is whether dark matter is cold or warm. And one type of candidate for warm dark matter is stereo-neutrino. So just give you an idea, all the cold, warm, hot, it's really talking about, you can think about the mass of the dark matter, or you can think about how fast the dark matter moving. Hot means it's moving very fast, it's realistic, like neutrinos. And the cold dark matter is much slow and non-realistic. And warm dark matter is about at the keV level. That's a very popular candidate like stereo-neutrino. And a big consequence observationally you see, right, in simulation, if you use some kind of dark matter mass to simulate the universe, Milky Way-like scale, on the left, again, center right is where our Milky Way is at, and there's a bunch of these subhalos that are have the dwarf galaxy reside in. You will see that if you use warm dark matter, then a lot of these fine structures, the small subhalo, get suppressed or washed out. And so basically we can count the number of satellite galaxies in our Milky Way as a function of how bright these galaxies are, and use that to differentiate between whether dark matter is cold or warm. Oh, by the way, I would appreciate if you have any questions, feel free to raise your hand and interrupt me, and I'm happy to answer them. So what we do as astronomer, we use these telescopes. So we had a lot of these optical imaging surveys starting from Stone's digital sky survey, probably about almost 2 decades ago now. And what we're using now is something like a 4-meter telescope. So Sloan is a 2-meter telescope. 4-meter telescope is what we are using now. And in about a year or two, we'll turn on this one, which is an 8-meter time scale telescope. So we use this large optical telescope, try to survey the sky, going very deep and finding these satellite galaxies. And in particular, the one that's what I'm using now is the middle one. It's called a dark energy survey. It's a survey that tried to imaging about 1/8 of the sky from Chile. Yeah, and I'll mention this result from this telescope several times. So this is how big the camera gets on the sky. It's about 1 meter in diameter. Just think about how big. It's like the detector on your phone, right? Your camera on your phone, but it's the size of like 1 meter in diameter. In terms of the area it can cover on the sky, it's about 4 times larger than a moon in terms of the angular size. So we couldn't finish the survey, but we have been using it to find a lot of galaxies. So this is like the discovery, the cumulative number of dwarf galaxies discovered as a function of their discovery year. So before 2000, before any of these digital camera survey was turned on, we only know about 10 dwarf galaxies in our Milky Way, but the simulation predicts thousands of them. And there is a big crisis called missing satellite problem that it seems the cold dark matter has a crisis to describe what we have. But as soon as the digital camera survey turns on, the Sloan discovered about like 10 to 20 dwarf. And now with the latest one, we have another 30 dwarf galaxies discovered. So there's a lot of new dwarf galaxy discovered and also get confirmed. And that telling us that there's a lot of actual dwarf galaxies in our Milky Way. We just didn't see them in the past. So this is what we actually at now. What you see in this plot, the x-axis showing you the number of satellite galaxies. The y-axis showing you the number of the satellite galaxy. The x-axis showing you how bright those galaxies are. And we're expecting the theory from the simulation, which is this red one, and also this blue shaded one. That's what the simulation tells us. And then the lines here, the gray lines here is from observation. So actually right now, we think the observed satellite galaxies with some observational bias correction, matches with the CDM model very well. So there's no actually crisis with all these discoveries and also with a lot of new understanding of our simulations. And we think that the Milky Way satellite luminosity function can give us a strong constraint on the minimum mass of the dark matter. So this is kind of, again, how it's being improving our understanding on the constraint on the warm dark matter mass. So this is the mass of the warm dark matter. I think about 2 decades ago, we don't know anything. And then from the Lyman alpha forest probe, we know that it should be at least, the dark matter should be at least above 1 keV. And as time goes, now we have excluded all the warm dark matter candidates below about 6 to 7 keV. And again, I'm only talking about the Milky Way satellites, but there are all other different ways that it can use to constrain the mass of the warm dark matter. So this is one example. However, as I show here, right, in this simulation CDM, you can see there are maybe, if not thousands, at least hundreds of these dark matter subhalo there. But earlier I said, okay, we find about 60 satellite galaxies in our Milky Way. There's no crisis. Why? The reason is because in the simulation, we realize a lot of these subhalo are so small that they never get enough gas to let the gas to kind of concentrate and attract and then to trigger the star formation. So there are a lot of these really dark galaxies that never had any star formation happen. We cannot see them. So that's another big, improvement of understanding in the simulation end. One is we find more from observation, but another is we expect some of those we were not able to see them anyway. And that's why I reconcile the crisis or the discrepancy between these two ends. So then the question is, how are we gonna go measure those? This is kind of the dark matter mass function, right? Again, the mass as a function, or the number as a function of mass, right? So we are really at this regime, and we know this part, it matches very well with CDM, but we don't know how it goes. Is it really going up at the low mass end? We cannot really know that from the dwarf galaxies because we know those subhalo doesn't even trigger star formation. So how we detect these complete dark subhalo? If there's time, I'm gonna get to these at the end of my talk. Okay, so this is the first part. We use the number of dark matter subhalo to understand the nature of dark matter. The next I want to talk about is we use the shape of the dark matter to understand the nature of dark matter. So this is another simulation that's showing you a Milky Way-like galaxy and its surrounding subhalos in a CDM model and in a self-interacting dark matter model. So here we are trying to test particles, a possible particle like dark photon or any self-interacting dark matter candidates. You can see something very similar to the previous warm dark matter one, that a lot of structure get washed out. There's fewer dark matter subhalo here. But actually there's something you probably cannot see very well is showing in this graph. So this is showing you like, let's pick one dark matter subhalo or even the Milky Way here. We plot like the density of the dark matter density as a function of the distance to the center of the dark matter halo. So this is what this graph is trying to show, right? So x-axis is the distance to the center of the halo, y-axis is the density. So the CDM and the SIDM, CDM stands for cold dark matter, SIDM stands for self-interacting dark matter. You can see there, and the warm dark matter is also there, but it's actually exactly the same as the CDM. So what happened is because if the dark matter interact itself, then the density at the center of the dark matter will be pushed down and will have a flattened core. So we call this is a core profile for the dark matter, while for the CDM, it will give this cuspy profile. So whether the dark matter distribution is cusp or core will tell us what is the cross-section for this self-interacting dark matter. So this is something we're also trying to measure in astronomy and try to constrain the cross-section of a self-interacting dark matter. However, one thing make everything very complicated is what in the left panel or in the right panel, that if you have dark matter only and you have CDM only, this is actually CDM only, you will have a Caspi profile. But if you have the CDM plus barium plus all the star formation, everything happening, that will also naturally flatten out the distribution of the density profile. So if you really measure something flatten out, you don't know it's coming from the galaxy formation itself or it's coming from the dark matter. So we want to really distinguish them. And the way is going to dwarf galaxies. Why? Because the smallest dwarf galaxies has the least star formation and has perturbed the least by all the galaxy evolution. So we want to find these cleanest galaxies that has a lot of dark matter, very little stars, and then try to measure this Caspi profile. And if we still get a core profile, then it's saying dark matter might interacting with each other. Okay, so this is kind of, again, state-of-art constraint that we get. Again, I talk about the satellite galaxy from Milky Way, but there are other ways like galaxy rotation curve, galaxy clusters, and these are like different lines of the cross-section constraint. So right now, we can rule out everything with cross-section bigger than about 1 centimeter square per gram. So these are the plots you probably see from direct detection and indirect detection. Often they are showing something, one on the cross-section, but on the direct detection, it's showing the cross-section between a dark matter and a standard model particle. In the indirect detection, it's showing the cross-section between 2 dark matter. Right, and it's an annihilation cross-section. And we have something like this for the astronomical probe. So one for these 2 particular model, one is warm dark matter model, one is SIDM, the self-interacting model. So right now we can exclude everything in this area. The dark matter has to be massive than about 6 to 7 keV and has to have a cross-section below about 1 centimeter square per gram. So I just trying to put them together. And we talked about some of the candidates here and some of the candidates here. Now I also want to talk about that what we try to study is more than just those branches. I'm going to touch a little bit on the microscopic part on MACHOs. So I'm going to talk about the primordial black hole. Or earlier, it has a very, probably if you know 20, 30 years ago, it's a very hot dark matter candidate called MACHO, which stands for massive compact halo object. So MACHO got revived recently. It actually is almost dead, I would say, since there's a lot of surveys in astronomy trying to see, and they think that MACHO doesn't explain the abundance of dark matter in the universe. But it kind of revived because of LIGO. This is like what LIGO detected for all the black holes. And if you look at the mass, there's a huge amount of black hole detection is at about 10 to 30 solar mass. And so the question is whether it's possible these dark matter, these black holes. So these black holes are not a regular black hole like the death of a star, right? Because we already know. This can be that, but dark matter cannot be just regular black hole because we know that dark matter is not baryon. It's not just the death of a star. It has to be something different. So we think that if they are black hole, then have to be something like a primordial black hole, which means they formed at the very beginning of the universe, right after Big Bang or together with the Big Bang. And those just formed and never, those are the black hole that formed at that time. It's not from the evolution of the star. So the discovery of all these black hole merger from LIGO make people wonder, are these actually primordial black hole? And they are the viable candidate for dark matter. So this is some work I did, and I connect to also the dwarf galaxy part. So why this is interesting? This is like the MACHO kind of constraint that we have. So the y-axis showing the fraction of MACHO can be dark matter. 1 means that can be dark 100%. 0 means none of them could be. So if we block out the entire area, that means that MACHO cannot be dark matter in this mass regime, right? So here the MACHO mass is between 1 solar mass to 1,000 solar mass. At the lower end, below 10 solar mass has been ruled out from the MACHO and EROS experiment. Those experiments basically do microlensing. They look at the stars in the LMC area and try to see the light curves, how bright the brightness change, and to study like whether there are MACHO there. And for the massive one above about 50 500 solar mass, it has been ruled out by the white binaries. The fact that the observations show there existence of some white binaries can rule out the massive MACHOs. But there is a gap in between, which is around 10 to 100. That's exactly where LIGO is finding all of these black holes. So we're trying to see if there's any constraint we can put in this regime. And here comes to a dwarf galaxy called Eridanus 2. So this is one of the satellite galaxies in our Milky Way. And in the dead center, you probably cannot see very clear, there is a cluster. So we zoom in a bit, there's a cluster in the center of the galaxy. And this is the smallest galaxy that owns its own star cluster. From the image, we feel it's in the center, although we really don't know the distance relative to the center of the galaxy. But if we assume that this is a cluster in the center of the galaxy, and based on the kinematics measurement of the galaxy, we know how much dark matter is in the center. And if dark matter is made of primordial black hole or MACHO in these waves, in this range, then the black hole will perturb the star cluster and dissolve the star cluster over the cosmic time. So the star cluster cannot survive for more than 5 gigayears. So the fact that there is a very old star cluster, about 10 gigayears or more than 10 gigayears, at the center of the star cluster in a very high dark matter density galaxy, we basically can put a constraint like this to rule out MACHO as dominated dark matter at 10 to 100 solar mass. So we can kind of close this gap here. But there's a few assumptions here. We are assuming that the cluster is just in the center, right? If the cluster just happened to be in the center in the projection, but it's a bit closer, it's definitely at a similar distance, but if it's off by several kiloparsecs, we won't be able to tell observationally. So it can close this gap. And so this is just in 1 solar to 1,000 solar mass range. I just want to show example. This is what's coming from all different methods. So what I showed earlier was this part that we're trying to put some of the constraint on. There are also micro-lensing event, white binary, which I talked about early, and also the gamma rays to rule out MACHO or primordial black hole as the dominated dark matter candidates across, again, about the 20th order of magnitude. This is in solar mass. And the dashed line is a projection from the future experiment. So Rubin, Roman, and the MEV, like gamma ray telescope in the space, those will also try to put more constraint. But there's still a gap that there's still the MACHO still can survive in a very small area in about 10 to the minus 15 solar mass. Okay, so I talked about, I think, 3 different varieties of dark matter and how astronomical observations can use to constrain them. And I also want to briefly touch the indirect detection part, because I mentioned at the very beginning that observations from astronomy in the sky can also help the constraint on the indirect detection part. So for indirect detection, the idea is the WIMP particles, the weak interacting massive particle, can annihilate or decay into standard model particle. The dark matter go in, and then something gamma ray or other standard model particle come out. And why this topic is so exciting or popular, because of the Fermi-lab result here, that this is what Fermi see of all the sky. A lot of these are not really associated with dark matter, it's all associated with baryon or other activity. But if you clean it up, this is what you see in the center of our Milky Way. And this is something we call the galactic center GeV axis. So in Fermi-lab at GeV at the center, there is some axis. There are many interpretations of that. It can be millisecond pulsar, can be some outburst of cosmic ray, but also can be really dark matter annihilation. Because if you ask where the highest density of dark matter, it should be from our Milky Way center. No, well, it can be also from other galaxies, but this is the closest one to us. So that's something we are expecting to see. So how dwarf galaxies can help on this? So these are the dwarf galaxies we observe. And because these dwarf galaxies have very little star formation, very little star, very little gas, and it makes a very clean astrophysical source to differentiate whether it's coming from these kind of millisecond pulsar or burst of cosmic ray, or it's really coming from the dark matter annihilation. So if we can see, if we think that this signal is coming from dark matter annihilation, and if we think these dwarf galaxies really are that dark matter dominant from the kinematic study, then we also expect Fermi-LAT will be able to detect some gamma ray signal from these galaxies. So this is what we did. So I just show one example called rectangular 2, that this is the map from Fermi-LAT. So from Fermi satellite, the LAT spectrum, the LAT instrument, and it's trying to map, and you don't see any much of this. So this is like, you can think of the axis of the signal. So at the center of the galaxy, you don't see any strong signal from gamma ray. And then as a astrophysicist, we calculate the dark matter density at the center of the galaxy. And this is what we produce from stellar kinematics. We combine these two, we can constrain the annihilation cross-section, that there's no detection of the gamma ray signal with such a high density dark matter in the center of the galaxy. We can put an upper limit on the annihilation cross-section. And this is what we have now. So the upper limit from dwarf galaxy is this black line. And those circles here are the galactic center axis signal that I mentioned earlier from our Milky Way center. So it's actually very comparable regime right now. These are the detection, right? If it's really from the dark matter annihilation. And this is from our upper limits, non-detection in the dwarf galaxy. And this is with about 20 dwarf galaxy. If we can double the dwarf galaxy size, so this is a projection, we will be able to push this line downwards with longer time of Fermi-LAT observation and more dwarf galaxy in our Milky Way. So if we can really push to here, then we can say about 3 sigma, we confirm that the detection of the galactic center axis, is not coming from the, dark matter annihilation. So that's kind of how the dwarf galaxy that we do can help on the indirect detection part. Okay, so I hope I have convinced you about a variety of science we can do to study the nature of dark matter using observations. I didn't go through all the model here, but there are a lot of branches we can go, either to the warm dark matter, self-interacting dark matter, or primordial black hole. And I think the observations and the simulations are continue to improve to constrain these dark matter models using the current or next generation telescopes and experiments. But I do want to say that this is not a thing that well recognized by the community. I want to show this plot, this screenshot. So in US, because that's where I come from before I moved here. So I did a lot of these kind of strategic planning in US community. There is something called a snow mass or P5. So every about 10 years, the DOE, the Department of Energy, and like a few agencies need to decide like what's the next generation experiment field to study all of these. And you might heard some of these are all physics experiment. And here are the ones that we do in astronomy, like LSST. But if you look at what science driver it is, dark matter is not there. Although I mentioned LSST is one of these imaging survey that I mentioned earlier. It was not considered in 2014 that they don't think astronomy as actually doing things related to dark matter. So we think we want to change this image and tell people actually we're doing a lot of study of dark matter. We're putting a lot of effort on this. So there is a snow mass for the next P5 right now. And we just put this on archive, I think last week or early this week. So I would encourage you guys to check this archive if you are interested in this topic. I think it gave a very good summary in talking about all different variety of energy level or mass range for the dark matter candidates and how we can use to study and what kind of instrument we don't build. Not only for that, for each different instrument or telescope or observatory or experiment, we are also trying to write these kind of science papers to talk about how we can use this particular instrument to study dark matter. So these are all very nice white paper for you to read if you want to learn about the field in general. So this is a paper on the larger synoptic survey telescope, or LSST, or sometime you heard of Rubin probably. That's the one that will start in 2 years. And this is another one that I help led is a spectroscopic survey, survey facility instrument that hopefully will happen in the next decade. And so we try to summarize all the science cases about dark matter related that we can do with this instrument. Also, in order to build such thing, I also just going to start a optical instrumentation lab at U of T in the AB building. And I would love to have more collaboration with people here because I'm sure the physics department has more optics and instrumentation specialists here. Okay. Oh, so I think I still have maybe 5 minutes. So just coming back, I asked this question earlier, right? About dwarf galaxy, we count the number of dwarf galaxy as a function of how bright the dwarf galaxy is. And that can tell us about the mass of the dark matter. But how about to the faint end? We cannot see these galaxies anymore. They are just dark matter subhalos. They don't ever form star there. So we cannot see them. Then how will we able to constrain the dark matter mass going to the smaller dark matter subhalos? We need to detect these kind of complete dark subhalo. And the way of getting that is to do something with a thing called a stellar stream. So this is another thing I worked on. So what you're seeing again is dark matter simulation with the center is the Milky Way, and then we have 10, I think, dwarf galaxy-ish dark matter subhalo here in orbiting around the Milky Way. And some of them get tidally disrupted and form these kind of ribbon-like structure. And these are the stellar stream that we call, so the galaxies or star clusters, they just get tidally disrupted and forming these kind of long linear structure on the sky. And we can see them. So this is again, the stream discovered in the dark energy survey. The movie, what you're seeing here is just a part of the sky, about 1/8 of the sky. And we're scanning through distance. So this is distance basically close to us to far away to us. And what you're seeing here is the density map. The bright means small density counts, number of stars. The black is high number of stars. So we count the number of stars at each different distance. And you can see as we're scanning through from about 6 kiloparsec to 60 kiloparsec, this is just some astronomical units. You can see some structure come out and then go away. And these linear structure, these are the stellar stream that we discovered using the modern imaging survey from dark energy survey that I mentioned earlier. So we discovered these streams. And what's the unique thing about the stream? So the stream should be coherent because when they get tidally disrupted and form this kind of linear structure on the sky. But if there is some dark matter subhalo coming by, although they don't interact with us other than gravitationally, but this gravity of subhalo passing by can form these kind of gaps in the streams. So measuring the density variation or the morphology of these stellar streams, we'll be able to measure these dark subhalos, dark matter subhalos that never form star. And that's something we're trying to get. And this is actually something already being observed. That's one example. This is a stream called GD1. The top panel is from observation. These are the stars belong to GD1. And you can see some spur feature here, we call it, and some gap feature here. And the bottom is from a simulation or modeling. Say, okay, what is, if something come by, perturb the stream and causing these kind of things, what kind of property that perturber could have? And that's what this work get. So they mimic the stream morphology on the top and then try to get the best fit parameter for this perturber. And this is what we have here. So this is what matches with a lambda CDM model. Okay, and these are where this perturber is at. So the perturber is much compact. This is size. You can see this is size, how big the perturber is. This is a mass, how massive the perturber is. So if it's coming from CDM-based dark matter subhalo, it should be in this gray shaded band. But the best fit model here is in this square box. So the best fit from the data is a much compact perturber compared to what the CDM model would predict. There are also different studies. Another study say this can come from another no dwarf galaxy called Sagittarius dwarf. But the point I want to show you is there are ways, the power here from the stellar streams to constrain the mass and the size of this dark matter subhalo. Even we never see stars in those subhalos. And that kind of connects to what I do Recently, in the past 2 years, I started this S5 survey, stands for Southern Stellar Stream Spectroscopic Survey. We want to map as many streams as we can and try to find these kind of structures. And one of them, oops, okay. So this is my group all over the world from, I think, Australia, UK, Chile, and US, and Canada. And so the thing what we use is a telescope in Australia, a formula telescope. The uniqueness, it has a fiber positioner that over 2 degrees that have 400 fibers. So the fibers can move within a few minutes and then point at where we want to observe, and it goes to a spectrograph. So in one exposure, we can observe 400 stars and get their velocities and stellar parameters. And so what we did is we observed 2 of the stream in this movie. If you can see it, one is this one, okay, and another is this one. So we think that time those are 2 different streams because one and another, there is a break here, and also one is much further than another. However, and this is what we observed. So these are the 2 streams here in a close zoom in look. So this one is here, one is here. And we identify the member stars from S5 for these stars. And there is kind of a break between these 2. However, with the observation, we find that this is a velocity, these 3 velocity in 3 dimensions, right? These 2 streams, this is along the stream, along this direction. So these particles, these stars are corresponding to all the stars here. So you can see the velocity in 3 dimensions, all seamlessly connected, although you show a gap in the morphology, but they don't have any problem in the kinematics. So we believe this actually is one stream, but somehow got perturbed. So this is another case that we find, but this stream is about 3 times further than the previous one. And so we are trying to find as many of these kind of signatures and trying to study statistically to understand the nature of dark matter. I think I'm running out of time. We need to finish at 3. Okay. So I want to say what the most exciting science discovery from S5 is not anything I mentioned earlier. It's like when people looking at what's the good example, searching for CMB, right, was discovered by engineer. Actually, we are trying to do stream, but the thing we find the most exciting thing from S5 is something called S5 HVS1. It's a high velocity star we find at about 1700 kilometers per second. I'm going to skip some of these. The most exciting thing we found is that it's not only that fast, it's also when we rewind its orbit, it's coming from the center of the galaxy. So the theory behind this is the following. If there's a binary star orbiting each other and they get close to the center of the Milky Way, there's a supermassive black hole, capture one star, and then eject another star. And that star gets to 1700 kilometers per second. And why it's so special, if you look at all the stars at a very high speed, this is all what we know in our Milky Way. HVS1, S5HV1 is much faster than any of the known ones. So we didn't expect to do this at all. And just let you know, most of the Milky Way star is at 50 to 100 kilometers per second. So this star is like 100 times, 10 to 100 times faster than most of the stars in our Milky Way. And it's much, much faster than any of the hypervelocity stars we know. This is probably telling us something special about the supermassive black hole also in our Milky Way. So with that, with a movie that showing you how the hypervelocity star happened, I will end my talk, but I wanted to give you a flavor about how we use astronomy to study dark matter and then connect to the black hole. And thanks for your listening.